Hi, this is Mr. Spone here, and we're going to finish looking at some simple Lewis structures for covalent bonds. In the last video, we looked at all of these molecules, and now we're going to look at some slightly more complicated ones, some double and triple bonds. So we have oxygen, O2, diatomic oxygen, and if we had two of them, we know that oxygen has 6 valence electrons. And each one has 6, so there's 12 VEs total that we have to draw our dot structure, and we want to try to get an octet. If we put these together, we're not going to get an octet, and I can show you that right here. There's only 7 electrons there, and the other one also only has 7 valence electrons, so we're not getting an octet. So what do? We cannot draw oxygen with a single bond. We could use a double bond. And if we put 2 valence electrons from each oxygen over here and we pair them off into a double bond, let's see what happens. Oxygen passes the octet test over there. There's 8 valence electrons in there. There's 8 valence electrons in that one because each oxygen is sharing 2 valence electrons with the other one. So there's going to be 2 separate bonds there, 4 electrons, creating 2 bonds. And we would draw this as a double bond. Each one of these represents 2 electrons. So oxygen is not singly bonded, it's doubly bonded. And we usually pair off the unbonded electrons. That's usually how we do it, and most of the videos and diagrams you'll see online will do this. Lewis structures predict this, but in general, this is not going to be true for oxygen. Oxygen has a quality called paramagnetism. If you made oxygen liquid and you poured it through a magnet, you get a bridge forming. So we know that these electrons are not paired off with opposite spins per Hund's rule, some of them anyway, and you'd have to look at molecular orbital theory to figure out why. But O2 is a diatomic double bonded molecule. But there is some quirk in upper level chemistry that requires more advanced specialization than we cover in high school to kind of figure out what's going on there. So for now, this would be a double bond, and oxygen exhibits this. Lewis structures have the advantage that they are simple. Molecular orbital theory is not. Carbon dioxide. Oxygen has 6 VEs, and carbon, of course, has 4. And if we put them together, well, we don't pass the octet test. A single bond fails for all 3 atoms. Carbon has 6, and each oxygen has 7. We don't have an octet in either one. So we're going to try a double bond. And we're going to put both of carbons. Carbon has 4 valence electrons. And we're going to put 2 of them here, 2 of them here. And we're going to connect that with a pair from oxygen. And again, carbon dioxide. It's going to work. We're going to have a double bond. So when we put this together and we do the octet test, carbon passes the octet test. It's 4 electrons and 2 from each of the oxygen atoms equal 8. And now oxygen has 8 and the other oxygen has 8. This is a very symmetrical molecule. And we would draw that structure like this. Call that each one of these dashes, or like this equal sign that represents a double bond, each one represents 2 electrons bonded together, shared. So that's 2, 4, 6, 8 electrons, 10, 12, 14, 16 VEs. And carbon started with 4, and each oxygen had 6. So 6 plus 4 plus 6 is going to be 16. We didn't gain or lose electrons like we were supposed to. Same number we start with, same number we're supposed to end up with. Let's look at nitrogen. Nitrogen has 5 VEs, and same story. If we combine it, well, we're not getting an octet there. So let's try a double bond for nitrogen. And let's put this together. Nitrogen still fails the octet test. So what can we do? Well, if a single bond doesn't work and a double bond doesn't work, we can try a triple bond. And this does work. Nitrogen passes the octet test. Diatomic nitrogen is a triple bond. Each dash represents 2 electrons. So that's how we would draw the Lewis structure for nitrogen. And remember, each one of those dashes is an electron pair, shared electrons, 2 electrons in a chemical bond. There is another way to draw this, and we're going to start drawing more complicated diagrams, so I want to show you a better way than just kind of fitting valence electrons together, because there's going to be different types of sharing and coordinate structures and resonant structures. Each nitrogen has 5 valence electrons for 10 total electrons. So each nitrogen is going to have 5, so we could work with 10 total valence electrons. We can't have any more than that. And we're going to start with a single bond representing 2 electrons. So this is 2 electrons here. So now I have 8 VEs left to work with. And I'm going to fill in the next 8 electrons. And because this is a symmetrical molecule, I'm just going to put 2 on each side. And we know this doesn't pass the octet test. So we're going to move some electrons in to form double bonds until it passes an octet test. So I'm going to take 2 electrons from each nitrogen, or 1 electron from each nitrogen, and move it in. Now I have a double bond, but it's still not an octet. There's 1, 2, 3, 4, 5, 6, 7 if I were to draw a circle around here. So that's still not passing the octet test. But if I were to take another electron from each nitrogen and move it in, now it passes the octet test. So that's generally how you want to draw these diagrams as they get more complicated. You just want to start with whatever whatever atoms you have, and you just want to connect it. You want to know how many valence electrons you have to work with, and you want to draw a single bond between them. That's going to be the best way. That's the way we're going to do it from here on out. And that'll help you draw dot structures a little bit better. And we just looked at in the previous video, we looked at single bonds, and now we just looked at double bonds and triple bonds. A single bond is going to be weaker than a double bond, which will be weaker than a triple bond. So nitrogen is pretty inert. The N2 diatomic molecule is relatively stable, and it doesn't really react with much. It takes a lot of energy to break that N2 apart in our atmosphere. And recall that our atmosphere is made up of 78% nitrogen. And you could think as each chemical bond as a rubber band holding it together. And obviously if you had 2 rubber bands holding something together, it would be stronger than 1, and 3 would be stronger than 2. So we can liken bonds to that scenario. So triple bond stronger than a double, double stronger than a single. There are some quadruple bonds, but generally we don't get to them. And you might think, well, how would you bond 2 carbon together? Can you have C2? Would it be carbon, all 4 valence electrons bonded together in a quadruple bond? Well, this doesn't actually happen. You'd have to look at molecular orbital theory, but there are some metals that have quadruple bonds. I don't think we really have any quadruple bonds in the representative elements, columns 1A through 8A. Usually it's the transition metals or other kind of metals. So, but quadruple bonds do exist, but generally we're never going to draw them. We're never going to have to worry about them. For the most part, we're going to have a lot of single and double bonds, the occasional triple bond.